No, that's the series. What's the function?
1 over...
Yes.
1 minus
1 over 1 minus x. Kick ass. Oh, Jeff. Memes. Oh, that's exactly what it was. So, I want to show you. This is what I was trying to find. There's a really cool video somewhere. I don't know what it is. It's probably me as I get older. For some reason, I'm having trouble finding things anymore. But there's a really cool video. It's got this big-ass speaker in the back of this car. Big-ass speaker. And they turn it on, they hit certain frequencies, and they kind of do slow motion, and you get these shapes of the oscillation of the speaker. This shape has a functional definition, sort of like, do you guys remember when you did parametric? If you took me for a pre-calc and we talked about Etch-a-Sketch, where you turn the dial and it's X and Y, but I'm the T controlling it, and it, you know. So this thing has a functional representation, but its functional representation is this. This is the first actual function that is purely defined by a power series. It does not exist in any other way. It's sort of like if we had the idea of sine, but we could only represent it as an infinite series. I don't know if you guys are with me at all. So 1 over 1 minus x. 1 over 1 minus x. Can somebody tell me, as long as the absolute value of x is less than 1, how can I write that function? What's another way to write 1 over 1 minus x if the absolute value of x is less than 1? Using an infinite series. You're all like, did we talk about that, Jeff?
Isn't it x to the n?
Be more. Tell me more. So you're not telling me that 1 over 1 minus x equals x to the n. That's not what you're saying. You're saying 1 over 1 minus x equals the sum from 0 to infinity of x to the n. Yes? If the absolute value of x is less than 1. And that is actually just, if I replace x with r, that's shit we've known for a while, right? But if I put the x in, it is now a function. 1 over 1 minus x is a function that at some point in your math career, you have done something with that function. To some degree, somewhere. It is a function. It has a representation as an infinite polynomial. Is everybody with me when I say that? Infinite polynomial. Where the shit am I coming up with that? Because what is that series? What's the first term in the series? 1. You put a 0, you get 1. Next term? X. So 1 plus x squared plus x cubed plus x to the 4th. So how else would I define that except an infinite polynomial? Yes. It is definitely polynomial, and it does an end. You guys kind of with me? I really want you. So what we're about to get into tonight is something I teased a while back. We kind of fell into this backwards. We didn't develop this. It was already there. We proved the sum of a geometric series, but we didn't look at it as, here's a function, let me make it into an infinite polynomial. We did not do that shit. You guys are all with me? We kind of fell backwards into this definition. That is a function that has an infinite series representation. And we all talked a little bit about why that's really cool. Polynomials are some of the absolute best functions. I know the best functions. Okay. Sorry. You guys with me? Okay. We'll do the worst impressions, but I do the worst impressions. So if I stop the infinite polynomial somewhere, I could get a decent enough approximation. So we're going to develop a process where I can start with almost any function. And I develop this process and we can make an infinite series polynomial out of it. In your head, you're probably going, what the shit is wrong with sine, Jeff? Why do you want to make an infinite polynomial out of it? I'm okay with sine. Right? Or some of you guys are like, sounds good to me, I don't like sine. You guys come with me? But for example, how the shit does your calculator do sine of 1.73? If you type that in your calculator, it will tell you an answer, yes? And you gotta make sure, because you're the human, that you're in the radians or degrees, whatever you need. You with me? Did you ever stop and think at all, how the shit does it do that? Because sine is an idea. It's a function, but how do I determine the outputs for each input? I've got to do all this weird ass trick shit if I'm going to do it by hand, yes? So the way the calculator is programmed is it actually uses the infinite series representation, and it just goes far enough until it knows it to the decimal place where its screen stops. So it does not calculate the right answer. It calculates the answer good enough to how big its screen is. Do you guys understand what I'm saying? Because last time, do you remember we did it and we got to 1 over 256 or whatever with that one example? And that was like way out. So that's what the calculator does. It has stored in it representations of functions as the series. And then it can kind of use it to figure out when you plug a number in, it does a polynomial. And not all infinite, it only has to go out like 10 or 20 or whatever, maybe not even that much, depending on your input. Let me stop for a minute. Are you guys at all understanding? The first level of use of these ideas of infinite series representations of functions is programming our stupid little calculators so they can do their wonderful shit and so that Staples can sell it for 120 bucks or whatever. You guys kind of with me? Yes? Okay. You can find free calculators, emulators online, by the way. You can't use a computer on your test, so I'm sorry. Too bad. Okay. So as we develop this idea, I need you to keep in mind there's at least a first level use. That's how we program calculators to do these funky ass functions. Natural log. It doesn't have a table of values that it stores. That would take up way too much memory space. Are you kidding me? It has a series representation that it just chugs in until, like I said, until it gets enough decimals figured out. Let me stop for a minute. I wrote to TI once, by the way. TI has me on a list somewhere because I should have saved this email. The email I got back was basically, do you work for HP? Stop trying to get our stuff. I was just like, how do you modify, I want to tell my students how you modify the Taylor series stuff to do your, I just want to give them a more, oh my God, where do you spy? Stuff. I was like, holy shit. Sorry, that wouldn't make a very good TV show. The intrigue of spying on calculator companies. But that was really neat. So, I feel like there was a question I did left unanswered, but if I did, let me know. So, we want to, I did leave one thing unanswered. This goes a step further. This is a function that only exists in this form. This is the function, right? So sine, how did we develop the sine function? We defined sine. It was the y side over the hypotenuse. And then we kind of developed a few things. You memorize a few things, then we can kind of fill in the middle. It's got to be in the unit circle. It's well defined, blah, blah, blah. This is the first function you have ever seen that does not have a representation other than this. That is what the function is. Okay. I'm going to stop saying that because by this point, if you don't really see what I'm trying to say, you're just going to keep saying the same thing over again. That's really neat as shit. So, real quick, just because, this will be a good little review, and I think that's what they're doing here anyway. Well, screw it. We won't do it because it's right here, Jeff. Do you see what they're doing here? What are they trying to do? Can somebody tell me what it is they're trying to do here?
Ratio test?
Yes. In order to find what? Well, yeah, the domain, but more immediately the interval of convergence, which you can then relate to the domain of the function since they've defined it as a function. So they set up their little ratio. You with me? What is one thing I would actually, does anyone see if I was grading this? Why I would take points off? Yeah. Stupid. Here, I'm going to write in here. Limit. It's my book.
It is.
Oh no. Okay. So now next semester you're like, oh, what the hell is this? Are you guys all with me? So this is trippy. I need you to understand. Even if you don't quite understand, this is trippy. This is the first time you've ever seen. We have this, which is a function that already existed that we put into this form. This is a function that is defined as a series. Okay. Bessel functions are like our go-to. There are some other ones, but they're all kind of related to this. So yeah, at that point it gets a little lame, but too bad. Now, so what I want to do for the bulk of today is develop this process I keep talking about. I'm going to feed the process of function. It's going to spit back infinite series, right? Or at least the first elements, and then I have to figure out what the series is. So we're going to start with a relatively decent little example. And actually, before we do that, I got to actually prove the process. So here is what we want this to do for us.
This is still 11:9.
No, this is 11:10. Finally. Okay. And while I'm thinking about it, what's happening next Tuesday? Quiz. Good. So what we want is we want to develop a process where if we are given, I shouldn't write this much, but I am. If we are given an f of x, we can find a0 plus a1 x minus x naught plus a2 x minus x naught squared, blah, 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 blah. Do you guys see how this is and if I write this as a series, is that cool? That is a power series. So I want a power series representation. Power series is another way to say infinite polynomial. I prefer infinite polynomial because that sounds trippy. We want to be able to get a process where if somebody gives me a function, I can find that. I can find that representation of the function. X naught, real quick, is the point where f of x exactly equals this, no matter what. Sure. So real quick, when you got a tangent line to a function, if I ask you to find a tangent line to y equals x squared, what else do I have to tell you? That's not enough information. Everybody, draw a parabola. Right, draw a parabola real quick. Doesn't have to be perfect. I'm sorry, on your paper. I love it. You're all like, this is weird. I'm like in Hogwarts or something. Maybe it'll stop.
It makes me think of you say no to those toasty parabolas. She calls them toasty parabolas.
Oh, toasty parabolas. Oh my god. Where was that from?
Ghostbusters,
Yeah.
the girl one.
Oh, the newer one.
Yeah.
Or I guess not the newer one anymore, but
Yes.
okay. With Kate McKinnon and all those guys.
Yes.
Toasty parabolas. I love that.
My father is
Let me think. What was in the middle of thinking about? Oh yeah, you guys are drawing a problem. If I ask you to find the equation of the tangent line to that curve, what have I not told you that you need to know? I have to tell you where. Yes? So the x naught is the where. I showed you last time, if you remember, we actually figured out the tangent line for 1 over 1 minus x at x equals 0. And I showed you that the result we got was the first two elements in the infinite polynomial. Because all this is going to do is it's going to improve upon finding the tangent line. That's it. That's what this does. What is the tangent line job? It's to approximate a curve near a point. And it's just a straight line. So it's like, I'll do the best I can, but what can I, this guy curves and I can't. Shit. So I'm gonna let him curve. I'm gonna let him curve a lot. Every higher degree allows for more curvature. Curve, concavity, then I could do the rate of change of concavity and the rate of change of that, and each of those is kind of letting it curve more and more so that it's able to fit this thing better. That's why if you find a tangent line and compare it to the first two elements of its power series representation, they're the same. I'm just adding more shit onto a tangent line function. Okay. Maybe. So, how the shit is this going to work? So that x naught there is exactly the same as me telling you find the tangent line at this point. So I'm going to say find the series representation at this point. Okay. So, did you get everything? So if I start with, I want this to be true, what I'm about to write down. I want this to be true. I want these two things to be equal. Well, let me do 3. Yeah, we're going to need 3. And then I go dot, 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 an x minus x naught to the nth plus dot, dot, dot. And it goes forever, yes? It's an infinite polynomial. You guys with me? So, isn't it true, when you find a tangent line, aren't you finding that? When you find the tangent line to a function, you found that, yes? What was a1 in that case? It was the slope, which in calculus terms was the slope in calculus is called the derivative. Okay. You with me? You with me? So whatever this process is, A1 better frickin' be equal to F prime. If that isn't true, I'm going to crumple this paper up. We're going to walk out in protest. Okay. Math is broken down. Jeff is old. He doesn't remember shit. Okay, let's see. Let's all see if Jeff remembers how this works. Okay, here we go. How do I figure out this guy? What is true about every other term except this guy? He's, of course, the constant. He's like the b from mx plus b, yes? Every other term has at least one x minus x naught, correct? No, not to bring up anything traumatic, but the immediate thing I think of is partial fractions. How do you kill every term except a nut? Let x equal what? If you let x equal 0, I get a1 times negative x naught plus a2 times negative x naught. No. How do I make this 0? If I make this 0, isn't it 0 everywhere? How do I make this 0? What would I let x equal so that this is 0? X naught. So I just plug x naught in. So for a given x naught, I know what this shit is, yes? This is going to be x. This is going to be 1, 2, 3. The only things I don't know are the a's. Those are the only things that will change. And that by itself is trippy. If I completely change my function, the only thing that changes are these coefficients. Okay. Give yourself some time. We haven't done any of these yet. Can you see if I plug? So now my whole process is, what the shit are these things? Because they are the only things I won't know. They're going to tell me f of x. They're going to tell me x naught. The only thing I don't know are those stupid a's. Right? A's, we normally want them, and now we're like, what are you doing there? Damn it. So first step, what is f of x naught? A naught. And what was the process in finding a tangent line? If I said find the tangent line to y equals x squared at x equals 3, what's kind of like a good first step? I want y equals x squared tangent line at x equals 3. Wouldn't you plug 3 in to see what your output is? Yes? That's all we're doing here. So this is find a series that represents f of x at x naught. So I'm going to plug x naught in. And it's going to give me my y-intercept. Okay. Not really a y-intercept it's going to be at this point, but you see what I mean. It's going to give me what this number is going to be. So how do I figure out a0? I just plug x0 into the function. Just go with me through this. I really want this to make sense, but I think the minute we do a concrete example of this, you're going to kind of see how this flows. You might be a little bit tripped up with all the stuff going on. How do I figure out, now here's the trick. How do I figure out A1? Why can't I just do what I just did? Is there any value I can plug in for x that kills everything except A1's term? No. You with me? Don't worry, you don't have to know the answer. You don't have to know the answer. Can you guys take the derivative of f? What's the derivative of f of x? You can do it. It's not that hard. What does this become? No. Do you see any x's here? It's a constant, totally. So what's the derivative of a constant? 0, thank you. What's the derivative of this? A1. Yes? What's the derivative of this? 2a2 times what? X minus x naught to the first, yes? Just derivatives, guys. Are you with me? We are just doing a derivative. We're doing a derivative of a polynomial. It's got a lot of weird shit in it, but I don't care. It is just the derivative of a polynomial. Let's do one more term. What would this one be? The derivative of this guy. Derivative of this guy. 3 comes down, 3a3 in front of this to the second. Do you understand? It's just power rule, yes? Why am I not worried about chain rule? Because what's the inside? 1x, so the chain will just have a 1, yeah? So I don't have to worry about him. And I'm going to do, here I'll do this one myself. The n will come down for the nth term, a sub n x minus x naught to the n minus 1 plus dot dot dot. That keeps going to infinity, yes? To the infinite term, I should say, not to infinity. So, stay with me now, come on. Look at that f prime. Is there anything I can plug in that will kill every other term except the one with a1? I can put x naught in again. So do you see I'm going to continue this process? So if I take one derivative, the thing I already know goes away, and this shit becomes accessible. If I plug x naught in, what happens? All of this other shit goes to 0. Yes? All the way to the infinite term. And all I have left is a1. Okay. All right, we're going to do the next one. Here we go. What do you think I'm going to do now? What? Take the second derivative? That's shit. Yes, we're going to take the second derivative. So go ahead. Take the second derivative of... So take the derivative of f prime of x. That would be the second derivative of f. Because then the same thing happens. I am trying to peel the shit away so I can figure out each a. Now hopefully you understand we're eventually going to get to a point where I can see a pattern so I don't have to do this to infinity.
Please.
Because we don't have that much time. All right, so let's see. F double prime. What happens to him?
Dies.
He dead. What happens to this one? 2a2 plus what happens to this one? 6a3, and then one of these are left, yes? And then I'll do this one again, n times n minus 1, x minus x naught to the n minus 2, dot, 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 forever, yes? So I'm just kind of keeping track of the nth term. Why am I doing that? So I have a chance to see what the pattern is. So how do I figure out what A2 is?
Plug with X naught.
Holy shit. Do the same thing we've been doing for the exact same reason? Yes? Yes?
At the very end, is that n times 2? At the very end of the
N minus 2. Sorry, I just keep bringing the power down, making the power go down by 1. Is that cool? I'm just applying the power rule. Yes?
I just want to make sure that's 6A3, right?
That is.
Okay.
6A3. Oh, taking class with me adds a whole other freaking dimension. I know. That's worse, Jeff. Oh well. So, what is f double prime of x naught? 2H. So what is A2? F double prime of x naught divided by 2. Yeah. What is A1? F first derivative of x naught divided by 1. So we're starting to see a pattern. I don't see how this guy fits in yet, but we will. At least these two hold to this. This is hopeful. I'm hopeful. Maybe there's a pattern here. Of course, I know there is because I've done this shit, but you can see how we can start to piece together and hope there's a pattern. Maybe some of you guys have done this thing enough that you see these numbers and they already look familiar. What am I going to do now? Holy shit. Third derivative. I'm sorry, not of that yet. Third derivative, this dies. This is 6A3 plus dot 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 n times n minus 1 times n minus 2 x minus x naught to the n minus 3 plus dot dot dot. Yes? Is everybody cool with this term? This is just the nth term. Somewhere out there, as I take derivatives, it's changing. What is this starting to look like here? Yes, in fact, these numbers should hopefully look familiar to somebody. What's f triple prime of x naught? This is not an x naught, by the way, sorry. 6A3, because everybody else has at least one of those in them. So what is f triple prime? I'm sorry, what is A3? And now what's a better way to write 6? What's 2? 2 is 2 factorial. 6 is 3 factorial. 1 is 1 factorial. So 0 is
1.
Stop it. So if I take 0 derivatives, it's 0 factorial. If I take 1 derivative, it's 1 factorial. 2 derivatives, 2 factorial. 3 derivatives, okay. You guys are doing good. So here's the result. The nth derivative evaluated at x naught is going to be n factorial times a n. Glasses would be good. There we go. I'm going to write worse. So therefore a n is equal to the nth derivative evaluated at x naught divided by n factorial. So if I come back to my representation I wanted, so it was this. But now I know an. I have an expression for an, yes? I love you guys. You're all like, dear God, man, make some sense. We'll do a concrete example to help us out here. To create, that's an n, by the way, yes? So that series is the infinite polynomial that represents the function I was given. So for a given function, I can construct a series. So the very first one I want to do with you is sine x. Because then I can revisit something from Calc 1 that you just had to, trust me, bro. We're actually going to prove it fully now. You just had to trust it. And some of you guys are like, whatever, man. Just tell me what it is. Okay.
Trusted you on that.
I know. I know. You shouldn't. You should always push me. First function I want to try this with. And by the way, just to remind you guys, I have the full thing up here, yes? Do you see what I'm saying? So you don't have to fully rely on your interpretation of my horrific writing to go by. You've got it on this handout, yes? Does everybody have this handout? 11:8 on one side, 11:10 on the other. Anybody else need that? Okay. Very excited. Very excited. By the way, has anybody ever seen me wear this? Yeah,
Yes.
T-shirt that's got this. I think it's got either eye pie, but both ways are the same. I wear a T-shirt. I haven't worn it in a while because it's kind of. I gotta get a new one. Poor little guy's a little beat up, but we're gonna be able to prove this in about probably by the next class. We'll be able to prove this statement. Has anyone ever seen this besides those of you who have seen me with my shirt? Why do math teachers and math people just kind of geek out over this? Because it's got the 5 most fundamental numbers in it. Additive identity, multiplicative identity, pi, complex number, imaginary number, e. So we're kind of like, whoa, look at that. So we're going to prove what the shit, where'd that thing come from? So if you've never seen it before, you haven't been worried about this until now. Sorry. So I'm going to alleviate the worry that I just put into you. Okay. So let's try this. Let's try this whole weird shit with sine. Poor little sine. Because we are the pioneers. We want to make a calculator that we can charge a buttload of money for, but we needed to be able to do sine of 1.73 or something, right? So what we're going to do is we're going to make a polynomial. And like I said, our screen's only so big. So do we ever need the exact right answer? No. That's the thing students don't even think about, and I don't blame you, because you're just like, why would I think about this stupid thing? But since the screen stops, they could do all these shortcut things in the background to get a good enough answer. Maybe? Okay. So, how does this process work? Well, let me write down what we want. So I want to be able to write sine x as this. Yeah, let's write it down like this first. You could do it, Jeff. Well, let me make this clear. I'm going to do this around x equals 0. So our x naught is 0. Is that cool? And you're all like, whatever, dude, do it. Jeff, you could do it, buddy. Let me write this again, just because I suck at writing. Okay. So therefore, I've got an idea of what to do. All I need to calculate is my derivatives. Do you see that? Everything else is basically there. I can throw shit in for this, I can figure that out. I mean, all I need are my derivatives, yes? And this really should be, this is my fault, this should be in little parentheses to represent that it's a derivative. I gotta remember that. Okay. Not a power. Yes, that's why I wrote it again, because it's a 0. So the x naught is the point at which we are developing this series. Just like I have to tell you a point at which to find a tangent line. Exactly the same reasoning. And by the way, let's do this. Since I feel like a lot of you guys have forgotten we did this, just watch real quick. If I want to find the tangent line of sine x at x equal to 0, I would first plug x equal to 0 in, and what do I get? Wow. Sorry. That was so neat. I got 3 distinct answers in a row to the same question. Sine likes y, 0 degrees is on the x-axis, the sine like it there.
No,
So therefore that is,
0.
there you go. Little sine turtle likes y, don't like x. I'm far away from home, I'm all the way in my shell, yes? No? When I'm on the x-axis, sine likes y, really far away from where I like it, I'm all the way in my shell. 0 of me is out. As you get closer to home, I start to peek out, and when I get up to y, I'm happy. I'm all out. All right, phrasing. So sine of 0 is 0. Okay. What do I need next to find the equation of the tangent line? To find the equation of a line, I need 2 things. I need a point and the slope. And Cash is now like, I remember, man, it's the derivative. Yes. So what is the derivative? Holy shit. And what is the derivative of that at 0?
1.
1. So what is the tangent line? What's the slope? 1. And what's the y-intercept? 0. So the first 2 terms of our series better be a 0 and an x. Yes? Or else we could throw all this out. We can go home early. Right? You can report me to my dean and say, I don't know about him, man. Yeah, give me an A. We'll be okay. Okay, bye. Okay. So here we go. Now I feel a little, now I'm like, oh shit. So here's what we do. We're going to develop our derivatives. We already did this just a second ago, yes? Get out of there, 1. So I'm evaluating, I'm going to find them, and then I'm going to evaluate them at the point I was given. In this case, it was 0. So what we just did was all the work we had to do for the tangent line. So all these, and the name of them, by the way, I keep hesitating to say the name, but when I make a power series representation of a function, we call it a Taylor series. To give props where props are due, when the point I plug in is 0, we call that a McLaurin series. Because both McLaurin and Taylor came up with this idea at the same time. McLaurin focused on 0 inputs, Taylor focused on any input, so we give them both props. You guys kind of with me? So when I say McLaurin series, it's just the Taylor series where I put in a 0. Taylor series is the general idea of finding an infinite polynomial for a function. So this is officially a McLaurin series, because I'm putting a 0 in. Okay. What's the second derivative? What's the derivative of the first derivative? What's the derivative? Negative sign. Now we get some neat shit. So what's f double prime of 0? It is what again? 0. Sine of 0 is always 0. So you start to see a pattern, yes? Good. And isn't that going to keep cycling like that? Are you guys with me? Okay, good. So let's look at this. And just to show you, on your little handout, as you do your homework, it's a really, really smart idea to have this sitting next to you. But let's use this as a template here. Yes? We've got this information. Can you do this, Jeff? We're going to find out. So this is just my, oh, by the way, so I kind of differentiated these. This is the Taylor polynomial that stops somewhere. This is the Taylor series that goes forever. So this really should be ... Jeff. You'll get it right someday, dude. Blah, blah, blah. Okay. So let's look at this guy instead. Sure. All right, put him underneath. So f of 0. So let me write this down. Here we go. Sine x equals f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed. Okay, let's see if that's enough.
So is the x minus a to the n, is that just like our variable, or,
X is our variable.
okay,
A is the point we're given, sort of like find the tangent line at the point A equal whatever, yes? So A is like x equal A, that's what we're building this around?
okay,
Okay.
so is our a 0 in this?
Yes, in this case, 0. We were
Okay.
given at 0. So on the paper, I replaced x naught with A, just because I thought it was easier to look at. Okay. That, if I replace f prime with m, which is what it is, that's just the stupid tangent line we got, yes? So too bad for you, we're not going to leave, because we got it. So let's see, what do I get? F is 0, 0. F prime is 0, 1. F double prime is 0, 0. So this whole thing here is 0, yes? F triple prime is 0, negative 1. Is that enough for you to see what's going to happen if I continue? I did 4 because then you see it starts over again. Isn't it going to, what would the next derivative, what would the fourth derivative be? Positive sine x, so it kind of starts over again, yes? So can anyone tell me the next 2 terms that I don't have to calculate, I can just see from the pattern? What's the next term going to be for sure? 0. And what's the next term going to be after that? Oh, what am I forgetting? Jeff, what are you forgetting, buddy? I forgot my, no, I haven't forgotten anything. Oh, yes, I did, right here. This is over 3 factorial, yes. So what's this going to be? Forgot this guy.
To the 4th
No.
over 4.
So no constants, x to the first. No x squares, x cubed. No x to the fourth.
Oh, x to
So what's going to be on the bottom?
5 factorial.
Kick ass, yes? I don't care what function you're given. That is fundamentally the process. Might you have to do more terms before you can see a pattern? Yes. All right, let me stop right there for a moment. So what have we actually figured out? And you're all like, yeah, man, that's my question. So let me clean this up a bit. Try again, Jeff. Sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Can somebody figure out the general pattern? How do I write this as this form? That, by the way, well, this is x to the first over 1 factorial. Kick ass. So real quick, you're going to see this. You've already seen this, but not like a ton. So it's okay if you forgot or didn't notice this. What is true about every power and every denominator? They're the same. What else is true about them? They are only odd numbers. So when n is 1, I get 1. When n is 2, I get 3. When n is 3, not 3, Jeff, you can do it, Jeff. When n is 1, this is 0, this is 1. When n is 1, I get 1. When n is 3, I get 3. When n is 5, I get 5. But if I want to just do it like this is the first term, this is the second term, this is the third term. When n is 1, I get 1. Let me even do it better. When n is 0, I get 1. When n is 2, I get 3. When n is 3, I get 5. Can you guys see 1, 3, 5? Aren't they 1 away from double something? So this, let me just tell you. How do I represent an odd number? Either 2n minus 1 or 2n plus 1. That's a definite odd number, yeah? Because 2n is even, plus or minus 1 is odd. So this will be x to the 2n. So if I want for the 0th term, I want it to be 1, I need this to be plus 1. So when n is 1, I'll get 3 and 3. Do you guys see that? When n is 2, I'll get 5 and 5. Do you see the idea with sine is, since there was every other one was 0, I can sort of compress it and then make a more direct definition. Now here's what's really cool. All right. Is everybody, all right, listen, this is your first time you've ever seen this as far as I know. Did we recapture the tangent line? Yes. What did we get for the tangent line? Sine x equals x. Yes? Yes? And that's the first piece. But do you all agree with me that very quickly the tangent line is going to lose touch with the sine? It's not going to do a good job of approximating it, yes? So if I keep tacking more terms on, that enables it to curve and kind of hug the sine graph better. If I go to infinity, it will become the sine graph. That last part is the trippy ass part. So let me ask you this. So this is a truth. This is a thing that we know. Unless I ask you to on a test, you don't have to rederive that. You just know it. The same way we know 1 over 1 minus x is equal to the sum of x to the n if x is less than absolute value of x is less than blah, blah, blah. So what I want us to immediately do with this before I show you a use of it is it even useful at all? If the interval of convergence is just 0, screw it. You guys with me? If this only works when x is 0, it's not useful. Can we figure out the interval of convergence for this? What's the process I go through? Yeah, ratio test. Okay. So I got this here. Then I want to set up my ratio test. How do I do it? What do I put here? This is where you got to be careful, yes? What do I do to figure out the next term? I replace n with n plus 1. So the mistake people make is they'll put 2n plus 2. That is wrong. It's 2 times n plus 1 plus 1. Yes? So replace n with n plus 1. And then I multiply by, of course, the reciprocal, so I don't have to divide and make a big-ass fraction. Nobody wants a big-ass fraction. Nobody got time for that. So I got to do a little simplification there first, yes? To see how much is there so I can see how much cancels. So can you go ahead and simplify that business? I'm tired. I'm going to take a break. What's cool is these are both the same, so whatever one is, I'm not going to know the other one. So what do you get when you simplify this? 2n plus 3. So this will be 2n plus 3 factorial. So now I know how many x's cancel, and I know how far I've got to go with my factorial rewrite, so I can see how much of that cancels. Does everything I just said make sense? Why start now, Jeff? So how many x's, let me ask you this one. How many x's are left alive? 2 of them, good. And where are those survivors? On the top. Now, how do I rewrite this guy? You all agree this is the bigger one. So he's got more terms than this one does. 2n plus 3? 2n plus 2? Good, because I've matched this guy now, right? Now this cancels. Now here's the really, really, really trippy thing. What do you get for that?
Zero?
Yeah. Right? X can only be finite. And eventually these guys kill it, whatever it is. Yes? These guys get big. It's n squared on the bottom, and the top is a constant for some value of x. So this limit is 0. What the hell does that mean? No. The opposite. When is that doing what it's supposed to do? What is the result? How do you interpret the result of your ratio test?
With an absolute value.
Absolute value is built in. So we got 0. What's got to be true about the result we get? It has to be
Less than one.
less than
One.
1. And like Moises just said, because he's like, come on, Jeff, step it up. He said, Jeff, obviously, that makes it all real numbers. Yeah, because does it depend on a value of x to make the result less than 1? No. I don't give a shit what x is. It's always 0. So it always works. So this, I need you to understand this. The 1 over 1 minus x kind of sucked because it only works if absolute value of x is less than 1. That is very constrained. Yes? Sine x, its power series representation, its Taylor series, in this case McLaurin, works always for any freaking number you want to plug in. That kicks a lot of ass. Some of you guys are like, I feel like it should be hitting me hard. That's all right. Just go keep going. All right. So here's the immediate thing you can do with this. Does anyone remember what this is?
Oh, shoot.
1. You've never been able to prove that, ever. You've never been able to prove that
Yeah, we get to.
until now. Because what is sine x equal to? X plus x cubed over 3 factorial plus x to the 5th over 5 factorial, right? Should be a minus in there, Jeff. There it is. All over x, yes? You with me? That is a true statement because sine x equals that no matter what x is, yes? Let me divide by x. I left my limit out. You can do it, Jeff. No, you can't. You're too tired. I'll make it. Divide by x. 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial. My blah, blah, blah. Yes? If I let n, I lost my n. Jeff. X, X, X. Okay, for a moment there, I'm like, oh my God. Sorry, I wrote it in terms of x, so it should be x. You guys with me? So if I let x go to, sorry, this is, oh my God, I love myself. Okay, give me a second. I gotta reset. Okay. X goes to 0. We're doing so many infinity things nowadays, I just forgot. Okay, x goes to 0. This is supposed to be 1. And sure enough, if I let x go to 0, what do I get? Every single term after this has at least one x in it, yeah? In fact, at least 2. So if I let x go to 0, I do get 1. All right, now that one I agree. That was less
But if x is
impactful than it
going
could have
to
been.
0, isn't the bottom 0?
No, that's the whole problem, correct? That is why, again, that should not trip you up. What form is this in?
It's a ratio.
Huh?
Fraction.
True, but it's in the form 0 over 0.
Yes.
So then we could do L'Hopital's rule, but to be honest, I don't think anybody here could really fully explain to me why L'Hopital's rule works. So this is a concrete, you can see it, proof that the limit as x goes to 0 of sine x over x is 1. You can see the shit happening because we just proved that this infinite polynomial is sine x. They are equal to each other.
Okay.
All right, again, I'm sorry.
Now what about the bottom?
I feel like that magician is like, I should retire. Every trick I try to show you, it's nothing. So go ahead.
I'm tripped up about the fact that like when at like the step that you took after where'd the bottom x go?
Oh, I divided by x. Doesn't every term have an x in it?
Yeah.
What is x divided by x? 1. What is x
Okay.
cubed divided by x? X squared. X to the 5th divided by x. X to the 4th.
Apparently I need to reset my brain.
I'm with you. Okay. Now that's, I'll agree with you. It's not the most amazing thing that you've ever seen. To me, what's more impactful about these Taylor series is that is how we program our calculators to be able to do all this shit they do. So what I want you guys to do is I want you to do everything we just did, but I want you to do it for cosine. I want you to develop the McLaurin series. So this would be around 0, yes? Or you can say A equals 0, whatever you want to call it. I want you to build it around 0. So it's officially, we're going to give props to McLaurin. All right, let's see this grade going. Thanks, man. So figure out the Taylor series, the McLaurin series representation of cosine. You just follow exactly what we just did with the beautiful notes you took on what we did. While you're doing that, I'm going to prepare something. I must prepare. Let's see. You guys at home can see what I'm doing. Oops. That's better. Let's see. Yeah, that's pretty impressive. Impressive. Okay, so I can go for that. Okay, I like it. All right. Whew. So this is going to become kind of like, you're going to be doing this a decent amount, not like a crazy amount, but quite a bit. You're going to have a bunch of problems. We're going to be doing this, making a big list of your derivatives, evaluating them at the point you were given, and then setting it up. Yeah? Okay. So not surprisingly, we know cosine and sine are offset by 90 degrees from each other. Their outputs are offset by 90 degrees. They get the same numbers, just a different order, yes? Not surprising. But what's really, really nifty, and if it's just nifty to me, I'm okay with it because it's freaking nifty as shit, is that all the terms that were missing from the sine, we're gonna see where they went. Don't you agree that when we developed sine, there were some missing terms? I was missing a constant. I was missing a squared. I was missing a fourth, yes? So how the shit do I go from here? You're lucky you got this thing, yes? So to figure out cosine x, it would equal, I don't know, have you guys gotten to this point yet? I'm sorry, I don't want to get too far past you. Try to put that together into the first few elements of the polynomial, yes? Let me do cosine, yeah. Okay, that's all right. You do that. Maybe we'll do one more. Oh, what would that be, Jeff? Oh, it should be 6 bar. That'll be 720, I believe. I think. All right, so does somebody have the beginnings of this? What's f of A? A is 0 here, right? So what's f of 0? 1. What's f prime of 0? So I'm just going to kind of skip. Well, let me put him in here. Plus 0 times x minus 0. What's f double prime of 0? F double prime is a negative 1. Yeah, so I got you. Negative 1 over 2 x squared. Yes? And then, of course, I get another 0. Yes? I'm going to do one more term just because, and you should be able to see what it's going to be, because this would be like 1 over 0 factorial, 1 over 2 factorial. So this will be 1 over 4 factorial, x to the 4th. Okay. Well, I went even further, but you'll see. I went even further on here just because I wanted to. So if I want to write this a little bit better, take all those zeros out, because who needs them? I get 1 minus x squared over 2 plus x to the 4th over 24. Yes. And just to put underneath it, sine of x was x, I believe, plus, Jeff, you've forgotten all of this. X cubed over 3 factorial plus x to the 5th over 5 factorial. So you see how it's kind of neat? They kind of have what the other one's missing. Okay. So those two are Taylor series, more specifically, McLaurin series that we just know. Just like we know 1 over 1 minus x, blah, 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 blah. Okay? So let me show you again. I've shown you something like this once before. So here is cosine. This is the tangent line at 0. It's doing its job beautifully. Would you agree? Near 0, if I zoom in there, it does a great job. It does the best a line could do. But very quickly, it screws up. It gets very far away from where it's supposed to be, yes? So if I go to the next level. If I incorporate the next thing, do you all agree that's better now? So that is curved. It actually hugs the thing much better for longer. At this point, the green is only this far off and the blue is that far off. So just adding the next term suddenly made it expand how long it's good. And of course, if I add the next term in, shapow! Even better. So the green was good till about here. This purple is good to about here, yes? And then finally, if I do this one, now obviously it goes on forever, but screw that. That's pretty damn good. Now, real quick, that's getting to be a really funky looking dude, isn't it? But yeah, he's a combination of all these weird divisions of powers of x and so forth. Yes, x to the fourth over whatever, blah, blah, blah. This kind of looks like mathematical Cthulhu in a way. Anyway, sorry. So if I kept going, it would just hug further and further and further out. If I went to infinity, it would perfectly match forever. That is really trippy. So this did it as well as it could when it wasn't allowed to curve. Then I allow it to match sort of like the next level, the concavity. Then I allow it to match how much the concavity is changing. Then I allow it to match how much that is changing. So every time I do that, I'm kind of allowing it to curve in another direction. Yes? So that's why it's able to hug this function. Okay, so let's do this one together real quick. What do I have on this paper, by the way? I always forget that I've made all these example problems. What do I have on here? Let's see. Yeah, all right. So every now and again, I'll ask you a very pointed question. Can anyone identify what is easier about number one than what we've been doing? I only need you, huh? Well, okay, centered at one actually makes it a little worse, but for natural log, it's good because I can handle a zero input, right? So that's past Jeff actually being awake and saying, nope, we gotta make a one. So it's not a McLaurin polynomial, correct? So if I stop in my Taylor series, I officially call that a Taylor polynomial. Series means infinite. If I just say Taylor polynomial, that means I'm stopping somewhere. So I just have to go out to the third degree term. Yes? And you all see why I can't do a McLaurin for natural log, because what's natural log of zero? It's undefined, it's negative infinity is what is approaching. Yes? Okay. But what I really want you to focus on right now is, yeah, cool. Number 3. We'll do the second part of this together. Are you guys, listen. I'm pretty sure nobody here is completely comfortable. Are you feeling a little better about this process than you were earlier? Once you see some concrete examples, obviously, if I'm you, the thing I'm worried about is, if I gotta see this pattern, am I gonna be able to see this pattern, right? So I'm not gonna throw a bunch of those at you, I'm gonna throw something that's kind of more obvious, but they get very difficult to see the pattern kind of quickly, especially when the function gets weird. The rest of it's just taking derivatives. When you're in Calc 2, you're like, yeah, let me take derivatives. Shit, yeah. Always better than, we'll go back to chapter 7? No, I'd much rather take derivatives. All right, I'm sorry. Do that. Do the one about e to the x. I'll stop talking.
What was this?
Oh yeah, so this is 0 factorial, 2 factorial, 4 factorial. In fact, the factorial matches with the power, which is really nice
Okay.
for those, yeah.
That's what I thought.
Right, from the form of it, Caesar, right? Factorials can always match with the power of 1. Yep. So be very careful, of course, f of 0 is 1, right? Okay. Now, listen, if you're having any trouble with your derivatives, that's a major problem. What's f prime? E to the x. So what's f prime of 0? 1. What's f double prime of x? So what's f double prime is 0?
1.
Okay. Right? You very quickly go, I don't have to do anymore. So now it's the question, can you put it together? So try to put together, you only have to go up to the third power, yes? Because I think I said I wanted the third.
Yeah.
Yeah. Okay. Yeah, you do that. Yeah, that's a good idea. All right. Yeah, okay. No, no, no. Okay. Good, good, good. Oh, yeah, of course. All right, so what are you guys getting here? So here I'm going to put approximately because we're going to stop. So of course, what's your first?
F is 0.
1. All right, so let's do it this way. Okay, so f of 0 plus f prime of 0 over 1 factorial x to the first plus f double prime of 0 over 2 factorial x squared plus, this is kind of nice. Look, look, look. Third derivative, 3 factorial, third power. Do you see that? Every term, the derivative I'm doing, the power x needs, and the factorial on the bottom are all the same number. Sweet. So if I put this stuff in, I only have to go this far, right? F of 0 was 1. F prime of 0 was 1. 1 factorial is 1. So I just get x. Is that cool? What do we get next? X squared over 2. Yeah, sure, sure, sure. In fact, let's do this. Yeah, I like that. Because we're going to... well, now for this problem we don't need it, but let's just put it for right now. What do I get here? Over 3 factorial, right? Very quickly, do you, if I kept going, what does e to the x, how does it seem to relate almost to cosine x and sine x? It's kind of like if I made the negative terms positive somehow in each of those and put them together, it would make e to the x, correct? So this is the less satisfying answer. So those of you who wonder why we do Taylor series, we get deeper connections between functions. That is the first level, and that led to the e to the I pi. We're almost there. I've almost got everything you need to be able to prove that. And you're all like, I'm okay if you never show me. Too bad. I'm going to show you. That was trippy. I thought it was in the room. Somebody's like making some coffee. All right. You guys got everything? Isn't that kind of trippy? That is trippy. They are connected. And it led to not just that stupid little equation, because that is a dumb little equation, to be honest. It led to everything that we do with it besides that dumb little equation. There's a whole branches of electromagnetics that I couldn't do as much with without this understanding. It is silly. So that is the less satisfying answer to people who aren't as into math, because that isn't an immediate real world application. But I understand the everyday simple functions, deeper relationship with each other when I do this kind of shit. Something we could have never teased it out without doing this. And then it had practical applications. And I think I told you guys that before. A lot of math is play around with shit, and 20 years later, like, oh, we need that. That stuff you guys are just playing with? We need that. Oh, good. Keep playing, okay. And then 20 years later, we got more shit. All right, sorry. I mean, that's the drunk history, but that is exactly drunk description of what actually happens. Okay. I'm not drunk, by the way. Am I? Not yet. Let me see. Okay. Oh my God. Okay. So the next level, is everybody cool? So for this specific problem, I can just write this like a normal polynomial, because that's what I wanted. Is that cool? So e to the x is approximately equal to that. Could you guys tell me where the approximation is best? Yeah, for x close to 0, when x equals 0, it's perfect. When you plug a 0 into both sides, isn't the answer perfect? Of course it is, because 0 is what we built this around. So whenever you build a series, a Taylor series around, is the one point it will be perfect for. As you move away from that point, your approximation gets worse. The further you go out in your series, the more it can handle you going away from that point. Maybe. That's the whole thing I showed you in the computer. When I put more terms on, it was able to go further out. So if I want to approximate, what did I say? E to the something. E to the 0.1. How do I approximate that? Put it in. This is approximately 1 plus 0.1 plus 1/2 0.1 squared plus 1/6 0.1 cubed. Right? 1 plus 1/10 plus 1 over 200 plus 1 over 6,000. Whatever, Jeff. We're just going to put in the calculator. Okay, man? All right. That's probably better. Wait a minute. So that'll be 30. Let me see. That'll be 31 for 6,000. That would be, would it be? Yes. And that would be 60. So that would be 60, right? No, 600. So it'll be 631 over 6,000. And then finally, so it'll be 631 over 6,000. I think. Oh, don't do it this way, kids. Did I even bring a calculator? No. So can you guys, is anybody doing that your own way? You don't have to do whatever the hell I just did. Are you doing that? Is anybody doing it? What'd you get?
I got 1.105.
1.105? Can you real quick, just for me, can you do 6631 divided by 6,000?
It's the same thing.
Huh?
It's the same thing.
Same thing? Cool. I just did the fractions. So you do it again for me, I'm sorry. 1 point. And then other stuff, but that's close, right? Can you now, in your calculator, just do e to the 0.1? Let's get the, we all know this is, now I can say this. When you put e to the 0.1 in your calculator, for more reasons now, you're not getting the exact answer. All the things off the screen, they could be completely wrong. And you'll never know because they're off the screen. So what do you get when you just put in e to the 0.1? 105, blah, blah, blah. Yeah. Pretty good, yeah. We only went out to the 3rd degree. Out of an infinite number of elements, we just had to go out to the 3rd degree. And it was good. Now, obviously, the further I get away from 0, the further I have to go out in my polynomial to still maintain a decent approximation. I love you guys. Who taller than each other? All right, what time is it? Oh, I got time. Ooh, too bad for you. So, let's take a deeper look at this for the moment. Here, let's look at this. Let's just play with this. Okay, that's as much as all right. Do you guys remember? So here, real quick. What is the square root of negative 1? I. Good. Yes? Just by definition, we did that just because we didn't want to look at square root of negative 1 all the time, so we just call it I. Therefore, so I to the first is I. That's amazing. I squared. No, it's negative 1. When you square, this dies, negative 1. So I, imaginary numbers are the first numbers where if you square one of them, you will get a negative number. You guys with me? Okay. My students, I showed you guys that neat little picture. Okay. Maybe I'll show you other guy, but too bad. You pick up somebody else. What is I cubed? How do you figure out I cubed? Don't I know I squared? What do I do to I squared to get I cubed? I multiply it by I. What is negative 1 times I? Negative I. Okay. And then what's I to the fourth? I could just square I squared to get I to the fourth, yeah? And what's negative 1 squared? 1. And then it just kind of repeats. It's cyclic. Very quick, just because. I don't know if everybody hears about this. Very quick. When I multiply 1 by negative 1, what do I get? Holy shit. So it's a 180-degree rotation. That's what it is. That is officially what it is. We just never tell you that for some damn reason. So when I multiply by negative 1, I rotate forward by 180 degrees. So what's negative 1 times negative 1? Visually, it's rotate again by 180 degrees. Visually, where do I end up? Back at frickin' 1. That's why negative 1 times negative 1 is 1. So what if I wanted to multiply by half of negative 1? I wouldn't rotate by 180 degrees. I would rotate by 90 degrees. I would be at this axis that somehow exists off the side of the x-axis. That is the imaginary axis. Now, very quick, because I just can't let it go. When we first came up with the idea of negative numbers, people said those were imaginary. Because they're like, if you have 2 apples and somebody takes 3 away from you, you have negative apple? This shit's wrong with you. Nowadays, especially college students, and I was one, you totally understand that negative numbers exist. Your bank statement comes, you're like, oh yeah, negative. Oh, I have no money, and they took money from me because I have no money. So that's life. Okay, gotcha. So, okay, I'm sorry. I'm sorry if that's hitting home, but I was there. I understand. You took $25 because I got no money. Where are you taking it from? Good job. Good luck. Okay, sorry.
My debt has debt.
Huh?
My debt has debt.
Yes, your debt has debt. I know. It's like, Dad, stop going out and gambling. So that is what imaginary numbers are. In fact, real quick, they called negative numbers imaginary. Now we know negative numbers exist. They called square root of negative 1 imaginary. Unfortunately, that stuck. And then when students hear that, they're like, they're making all of this shit up. They're just finally being honest. But imaginary numbers, they actually exist. There's entire branches of physics that you couldn't even start to do without the idea. Just simple voltages. When you unplug something that's still on, don't you get a spark? That's the voltage trying to maintain. It wants to keep it going. And you can't describe a voltage wave without imaginary numbers. I'm not going to get into that, obviously, but you guys kind of, sort of with me? So it's really bad that imaginary numbers get this bad rap, and you don't get to see them until you're in college, and then it feels like this esoteric, like this, oh, it's weird. No, it should be taught way sooner. It just be a normal part of life. with all that said, can you guys please take e to the x and plug an I into it? I'm sorry. Plug an ix into it. There you go. So if e to the x is 1 plus x, e to the ix is 1 plus ix, yes? Plus ix squared over 2 factorial plus ix cubed over 3 factorial. Is everybody with me?
Yeah.
So that level I'm just shoving shit in, yes? Shove that shit on in there. Now, ix is ix. What is ix squared? I squared is negative 1. X squared is x squared. What is I cubed? Negative I. So I get negative I x cubed over 3 factorial. One more up here. This would be plus x to the 4th over 4 factorial. Y'all with me? Do you see how these guys, I would not agree with this assessment. Would you say those are normal? What are those? No. The ones I underlined. One is x squared over 2 factorial plus x over 4 factorial. What is that a representation of?
The EDX.
No, come on. Just these parts. The whole thing is e to the x, just these parts. We just did it. Cosine. So these are cosine. Yes? Aren't each of these, if I kind of take the I and put it aside, what's each of these? I'm sorry, not you. I'm sorry. You're fine. There's a sine, yes? That statement is true. We just proved that statement. That statement still doesn't make sense, though. You take e, you raise it to an imaginary number, and you get trig. I'm surprised nobody flipped the table and walked out. That's it, man.
I don't have this right.
But you all agree. Now listen. I understand that better because I've used it before. I still don't quite fully understand it, to be honest. Right? There's a certain way you have to look at it. I've done a lot of shit. It's all about rotations. It's really neat. If I put a pi over 2, I'm rotating. So if I wanted to, what did I say earlier about if I wanted to rotate by 90 degrees, isn't that pi over 2? What do you get when you put a pi over 2 in? I. Isn't that what that is? That's I. So this is kind of like the rotational aspect of multiplying by -1. So if I put pi in it, I'm going to get -1 because that would be a full rotation. That would be what we normally call multiply by -1. If I put any other angle in there, I would multiply by that much of -1. If I put pi over 4, I would rotate by 45 degrees. Yes? I can notice some of you guys are like, oh my god, dude, stop. It's really, really cool. Really, really trippy. Nowhere near intuitive. No way in shitting hell would you ever go, yeah, exponential is going to be equal to cosine and sine and so much. No, there's no way in hell.
Wait.
What's up? So now if I do this real quick.
Is that what this thing is?
Oh, dude, yeah. That's there you go. Thank you, Sarah. On your homework sheet at the bottom is there's a comic called Foxtrot. They had a lot of math in it, but it's a really good comic, and they had math. So, I mean, come on. But, yeah, thank you. A lot of you guys probably looked at it and just were like, good Lord, whatever. but now she's asking what's cosine of 60 degrees. So here is the Taylor series of cosine, yes? Then she says, I'm paying you, I'm not paying you by the hour, so he just says the answer. Okay. So if you did this, it would come out to be 1/2, but of course, we don't have to do that. We already know what the answer is. Is that cool? So thank you, sir. I forgot I put that on there.
I was waiting until that came.
You almost missed it. So real quick, just to remind you guys, e to the I x is cosine x plus I sine x. So what is e to the I pi? Cosine pi plus I sine pi, yes? What's cosine of pi?
0.
No.
No, negative.
Negative 1. And what's sine of pi?
0.
Yes? 0. So you get e to the I pi plus 1 equals 0.
Yeah, oh, okay, see that is over, okay.
And that's what I got in the illustrative. Okay. And again, we like it because it relates all of the 5 most fundamental numbers that we have come across, discovered, or attributed things to. Additive identity, multiply, blah, 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 blah. Okay. Sweet. I didn't think I'd get there tonight. And you're all like, you didn't have to, man. Too bad. So very quickly, I will show you this. What is that? I don't know. I'm scared. Okay. Here. Oh, wow. Went right to the page. Familiar? First one we ever did. We kind of backed up into this one, though. We could verify this by doing f prime, f double prime, but let's not, because we already know it. Okay? E to the x, sine x. There's this cosine x. It's got the even stuff, so that's why it's got 2n, because that's even. Yes? Arctangent we could do. That is neat. Look at this. This is almost this, except it's not a factorial and it's not alternating. Oh, when I wrote that, I forgot the alternating, didn't I? I suck. I'll be okay. Oh, it is alternating. You'll be all right. You're double. That's okay. Natural log. Why do you think we would do this? Now, can I make a McLaurin series? Can I make, what's McLaurin series mean?
So that's like
I use an input of,
0.
am I allowed to use an input of 0 here? Yes.
Well, now you are.
So if I make a natural log of 1 plus x, I can actually get its McLaurin series. I couldn't do that if it was just natural log of x. Okay. So we have this big, long list. This one we're going to focus on next time. This one is trippy. This one's called the binomial theorem. Have you guys heard of Pascal's triangle? Some of you guys definitely have because I've shown you, but some of you guys have heard. Oh, beautiful. This is kind of like an extension to that.
Is that supposed to be k over n?
No, it's supposed to be k choose n.
Okay.
I'm not going to get too deep into this, but if you took any statistics, if I have k things, how many ways can I choose n of them? That's what that means. So I want to do last thing for tonight, and then we'll get out nice and early. Yes? Because I feel like I'm frying your brains, and my brain is fried also. So I don't want to do too much more to us. Irreparable harm to our brains. Oh shit, this is what I wanted to do, Jeff. Damn it, that's why you opened the damn book. All right, so if I take any of these, let's do e to the x. Yeah, because it's a nice one. If I take e to the x, just to kind of bring this back, and that's the sum, n equals 0 to infinity, x to the n over n factorial. That's a beautiful look at that. E to the x is a superstar. Real quick, just to get something we know, if I take the derivative of this, what should happen? What should happen? It should be the same. Yes? So let's try it real quick. What's the derivative? I'll do this side. Okay. What happens on this side? N?
Comes down.
Come on, yes. N comes down. Pass it around.
It'll be n minus 1.
Yep, sorry. So this will be officially n equals 1 to infinity, yes? Now let's kind of mess with this a bit. You guys all with me? Okay. Then what can I do with the bottom? Could something cancel if I did something with the bottom? How do I rewrite n factorial? N times, don't these cancel? Now, watch. When n is 1, what's this? 0. When n is 1, what's this? 0 factorial, yes? So, I've done this once before, at least once before. I'm going to start at 0 instead, which means this can start at n and this can start at n. Is it the same as it was before? Same as it ever was? So, of course, if I claim that I have a series that represents e to the x, it better do every damn thing e to the x does. And one of the most fundamental things it does calculus-wise is it's its own derivative. So if that didn't work, then that's not right, Jeff. Try again. All right. You guys all with me? So here's what I really meant to do. I just suddenly thought about that on the fly. So this is true. So what is e to the, what do you got, Jeff? I don't know. X squared over 3. What do you guys think? If e to the x is the sum of x to the n over n factorial, what is e to the x squared over 3? Yes! Sorry, I'll come back. X squared over 3 to the n, I need a summation symbol, Jeff, over n factorial. We've done that before, but not a lot. I did it maybe once or twice. If I have a power series representation and I change the input, well, I change the input. Not a big deal. If I say f of x equals 2x, what's f of y? F of x is 2x. What's f of y? 2y. What's f of a? 2a. So if I say e to the x equals this x, what's e to the stuff? It's this stuff, yes? I'm just replacing, just like we do with any function. And then I can finally, sorry, you're all, I said the magic word, you're like letting me out of here. Do you see how this works? X to the 2n? And then I could put on the bottom 3 to the n. Is that cool? Okay. So I had a different function, but I did not have to go through the whole process because I have it's based on a function I know. So there'll be a whole subset of homework problems that are like that. That's plenty. That's so plenty. Go for it. I'll see you guys. Don't forget Tuesday, quiz. First thing.